Welcome to the webinar on quantum computing applications in financial sector, co-organized by the Keene Institute at UNC Chapel Hill and North Carolina State University IBM Q Hub. I'm your host, Eric Geisels. I'm a professor of economics at UNC Chapel Hill and a professor of finance at the Keene Flagler Business School. 2 weeks ago, we had the pleasure of hosting Stefan Werner from IBM Research in Zurich. Stefan talked to us about machine learning, optimization, and derivative pricing applications using quantum computing. Today, we have the pleasure to host Isaiah Hull, who is going to talk about quantum technology for economists. Isaiah is a senior economist at the Swedish Central Bank. He obtained his PhD from Boston College. His research interests range from machine learning, macrofinance, fintech, and he's also involved in an interdisciplinary project of quantum computing applications for economists, which is a topic he will be talking about today. He's writing a textbook on machine learning using TensorFlow for economists and finance practitioners. He's also teaching machine learning on the DataCamp platform and is involved in a project tracking in real time the impact of COVID-19 on the economy. In fact, I was really pleased to see that there's a lot of overlap of research interests that Isaiah and I have. So I'm looking really forward to his talk today. A few housekeeping rules. At the bottom of your screen, you will see a Q&A tab. Please feel free to write your questions during Isaiah's presentation. At the end of this webinar, we will have a Q&A session where some of the questions will be fielded to Isaiah. It's really a great pleasure to host Isaiah today. Thank you to all of you who are participating, and I'd like to pass on the screen to Isaiah. Thank you.
Okay, thank you, Eric, for both creating this series and for inviting us to participate in it. So the title of the paper that I'm going to present today is Quantum Technology for Economists. We don't yet have a working paper available, but we should have one soon. So if you find the project interesting, please send me an email and I'll add you to the list. As soon as we have something we can circulate, I'll send it to you. So I work in the research division at Sweden Central Bank, and I'm working on this project with 3 co-authors who are outside of the economics discipline. So Or Sadeth is a computer scientist who works on quantum cryptography. One of the topics that we'll discuss in this paper is quantum money, and Or has actually constructed theoretical quantum money schemes and has evaluated the properties, the security properties of quantum money schemes. Eleni Diamante does work on experimental quantum cryptography, and she and her group were actually the first to experimentally implement a quantum credit card scheme. Joran Wenden is a theoretical quantum physicist who works on the physics of computing and has done interdisciplinary work to introduce quantum computing to both biology and chemistry. Okay, so what is it that we're trying to achieve with this paper? Well, we're taking the broad field of quantum technology and we're trying to identify the subjects within it that have relevance for economists. So broadly, we can divide quantum technology into 4 subfields. So there's quantum computing, which is concerned with the construction of computational devices, which are able to exploit quantum phenomena as a computational resource. There's quantum simulation, which is often used in basic research applications in fields like physics and chemistry. So sometimes to answer a research question that is concerned specifically with a quantum system, it would be best if we could perform that simulation in a quantum system. But if we're limited to using classical systems, then at best we'll get a approximate solution to that. The third subfield of quantum technology is sensing and metrology. And this is concerned with the production of high precision scientific measurement instruments that achieve high precision by exploiting quantum mechanics. And then there's quantum communication, which is chiefly concerned with the construction of secure communication channels making use of quantum phenomena. Now, within quantum technology, we're going to focus on two subfields of subfields. So the topics that we identify of interest for economists are quantum money and quantum algorithms. So quantum money involves the construction of forms of money that are secured against counterfeiting using quantum physics. And this level of security that's provided allows us to create forms of money that have properties that we're unable to achieve with any classical form of money. Quantum algorithms is a subfield of quantum computing. And here we'll try to identify all relevant applications within econometrics and computational economics. So most of our coverage here will be focused on low-level algorithms. So rather than portfolio choice and so forth, we'll focus on things like solving linear systems, which will probably be a subroutine to some higher level algorithm that we're interested in economics. Now we'll focus almost exclusively on the theoretical side of these problems. And the reason for this is that economists are closest to being able to understand and contribute to theory. We don't expect, for instance, that economists would contribute to the experimental development of quantum computers, but with a little bit of additional mathematics and notation, economists could reasonably contribute to the development of quantum OLS or quantum principal components analysis. Now, one of the differences between my talk and the paper itself is that the paper is intended to take someone who has a PhD in economics and finance, along with the background in mathematics that you'd receive to attain such a degree, so probability theory and linear algebra and so forth, and get them to the point where they can understand basic quantum money schemes and basic quantum algorithms at the low level. So they'd actually understand what it is that allows them to achieve a quantum speed up in an algorithm and how the algorithm is constructed down to the subroutine level. Now, we won't talk about that much here because there's not time to introduce all this preliminary material. But instead, what we'll do is focus at a higher level on concepts, and where necessary, we'll introduce some background material so that we can talk about a couple of low-level objects of interest. Now, the final thing that we try to do in this paper is to identify points of entry into the literature for economists. So there is, in fact, already papers being written about quantum finance and topics of interest for economists, but for the most part, economists aren't participating in this literature. So our goal really is to identify where it is that economists can contribute and where the interdisciplinary literature is, specifically in the areas that economists will have a natural interest in. Now we'll divide the talk into two pieces. One piece is about quantum money, one is about quantum algorithms. We start with quantum money, which we said was concerned with the construction of money schemes that are protected against counterfeiting by the laws of physics. Now, the very first quantum money scheme was introduced by Stephen Wiesner originally in 1969 and then actually published in '83. And the objective behind this paper was quite ambitious, which was to construct a form of money that was physically impossible to counterfeit by the laws of physics. Now, if we think about more familiar forms of money and how those are protected against counterfeiting, we might naturally think about physical forms of currency like bills and coins. Now, how do we protect, say, a $1 bill against counterfeiting? Well, we build into it physical features that we assume are costly for a potential counterfeiter to replicate it. So in the case of a $1 bill, we have raised printing on the bill. We have a special paper blend, which consists of linen and cotton and contains red and blue security fibers. And if we look at higher denomination bills, like a $100 bill, we have additional security features, which are both harder to replicate and can also be identified more easily by, say, a merchant who's checking to see whether a bill is counterfeit before accepting it. Now, if we look at the types of currency that we're increasingly using now, so digital forms of money, this can include things like private bank deposits and their transaction and their transfer mechanisms like debit cards and bank transfers, as well as cryptocurrencies. These are secured by cryptographic algorithms. And what underpins the security of such an algorithm is a computational hardness assumption. So we specifically assume that our cryptographic scheme won't be cracked because it's very hard to do some specific thing computationally. In practice, we don't actually have any certainty that that's true. So the reason that we think that it's true is because there are a lot of very smart people trying to come up with better algorithms, and in many cases, decades have passed and no one has been able to do this. So this gives us some confidence that this is very hard to do, but it could in fact be the case that someone has come up with something better and it's just not in the public domain. Now, an example of such a computational hardness scheme failing is the RSA encryption scheme, which is sometimes used to conceal information in bank and e-commerce transactions. Now, specifically with RSA, we assume that it takes sub-exponential time to perform prime factorization of integers. So this is slightly less than exponential time. But we know, in fact, that since 1994, we've had a quantum algorithm which allows us to do this in polynomial time, that is nearly exponentially faster. Now, we don't yet have quantum computers with sufficiently many qubits to implement this to crack the RSA scheme for integers that are as big as the integers that are being used to secure information about bank transactions, but it's conceivable in the future that we could, and this scheme would no longer work. So to reiterate, with classical forms of physical money, like a dollar bill, we have actual physical security features that protect us against counterfeiting. When it comes to digital forms of money, be they bank deposits or cryptocurrencies, it's going to be a computational hardness assumption, and we don't know for certain whether or not that's satisfied. Additionally, technological progress in the development of algorithms can make it so that that assumption eventually fails. Now, how does quantum money differ from this? Well, this shows a mock-up from Science in 1992 of a bill of the type that Wiesner originally envisioned. So here we have a classical serial number, which is stamped on a bill that is produced by the central bank. And this classical serial number is public information. So the central bank themselves record this number when they produce the bill. The person holding the bill can see the serial number, and in principle, it could be posted publicly, and that wouldn't undermine the security of the scheme. Now, in addition to this, the central bank also needs to generate some classical information and encode it in the bill in some way that it remains private. And so specifically, the scheme that Wiesner proposes is that we encode it inside of unentangled two-level quantum systems. So here, what's depicted is photon polarizations, but we won't talk specifically about the types of quantum systems that we'll use. In principle, any two-level quantum system could work. Now, there's one additional requirement of this scheme, and that's that the central bank that produces the bill has to encode this classical information in quantum states in a very specific way, and they have to write down how they encode that information so that when they check the validity of the bill, they perform a very specific procedure to recover it. And if we don't perform that procedure in the same way, then we can't recover the information. Now, that's the very high-level description of Wiesner. We'll actually give a complete low-level description in a couple of slides. Now, you might think, what is the difference between this and between a physical bill? So with a physical bill of the type we use now, we have physical security features, and we assume that those are hard to replicate. Now, a counterfeiter doesn't have to have the same machine that the Mint or the Federal Reserve uses to produce bills. They just need to produce something that looks sufficiently credible so that it will pass whatever security check is being imposed, whether it's a merchant accepting the bill or whatever the case may be. And we might think, can't we do the same exact thing with Wiesner's money? Can't we create a bill that, when you look at it, it looks about the same as Wiesner's money? Or when the Federal Reserve checks it, it passes the test, even though we don't necessarily know how the Federal Reserve encoded the information in the first place? And the answer to that is actually no. So since 1982, we've had something called the no cloning theorem, which was proven by Wouters and Zurich. And what this says is that if we have a quantum system that's in an unknown state, we actually cannot clone the state of that system. And this follows from the linearity of quantum mechanics. And it's actually, it holds independently of the quantum system that we're using. So it does hold for photon polarizations, but if we use a different quantum system to implement this, it will also be true. Now, in the preliminary section of the paper, after you walk through new notation and new mathematics, you'll actually see two separate proofs for the no cloning theorem. And this is actually quite trivial to demonstrate once you've been initiated into the literature. So you'll see that you can demonstrate this with about 10 lines of mathematics in two different ways. Okay, so I'll review very quickly a few things that Stefan said because in his presentation a couple of weeks ago, because this will help us to fully understand how Wiesner's scheme works. So we know with classical systems, classical two-level systems like a switch, we can encode a bit of information. If a switch can be on or off, we can encode a 0 as the off state and a 1 as the on state, and then we can check that switch to see which position it's in to see what bit of information is being encoded. Now with quantum two-level systems, they can also be in these pure 1 or 0 on or off states, but they can also be in an uncountably infinite number of superposition states, which are linear combinations of the on and off states. Now we specify the degree of on and offness using complex valued amplitudes. And one way in which we can completely specify the state of a quantum system is by using these amplitudes coupled with a basis. Stefan mentioned that there are two commonly used bases, the computational basis and the Hadamard basis. The choice of a basis is going to be arbitrary, but we do happen to have some useful relationships between these two bases. Now, a basis is going to consist of two orthogonal vectors. We can see the computational basis encodes the quantum state 0 as 1, 0 and the quantum state 1 as 0, 1. And we see that we can re-express this in Dirac notation. So here the 0 state is ket 0, the 1 state is ket 1. The reason that we do this is that the joint state of multiple quantum systems is given by their tensor product. And if we're doing analytical work, the vector that results from that tensor product is going to quickly become too big to work with on using pencil and paper. So we instead just use this this Dirac notation where we place the 0 and 1 in a ket. The Hadamard basis is another commonly used basis, and here we have plus and minus bases vectors. So the plus state is 1 over root 2, 1 over root 2, and the minus state is 1 over root 2, minus 1 over root 2. Now there are two useful relationships between the computational and Hadamard basis. So the first is that we can translate between the bases using a Hadamard operator. So if we take the plus state and apply the Hadamard operator, we get a 0 computational basis state. And if we apply it to a minus, we get a 1. And the same is true going from the computational to Hadamard basis states. The other valuable relationship between the two for our purposes is that the computational basis states are actually in equal superpositions of the Hadamard basis states. So the 0 computational basis state is actually in an equal superposition of the plus and minus states. Okay, so that's all the background information that we'll provide. Just a reiteration of, for the most part, of what was already said in the first presentation in the series. Let's talk about how Wiesner works at a low level. So the first thing that we do in Wiesner's scheme is the central bank takes a bill, it stamps the classical serial number on it, and then it generates classical information to encode in the quantum systems. So let's say it's going to use 20 unentangled two-level quantum systems. So it will generate 20 bits of information to encode in those systems. Each system will have a 0 or a 1 encoded. In addition to randomly generating that bit of information to encode, it'll also randomly generate a basis in which to encode it. So each bit will either be encoded in the computational basis or the Hadamard basis. If we draw a 0 and we draw the computational basis, then we encode it as a 0. If we instead draw the Hadamard basis, then we encode a classical 0 as a plus, and so on for a 1 and the minus state. Now, one thing that we said earlier about the computational basis states being superpositions of the Hadamard basis states turns out to be quite useful for this scheme. So if we take the 0 state, which is a superposition of plus and minus, and we apply measurement to it to see which of the plus or minus state it's actually in, it will actually behave probabilistically and snap into one of those two states. And since we have an equal superposition of the two, it will happen to be the case that it splits into the plus state with half of the time and the minus state half of the time. And the same is also true if we apply measurement in the computational basis to a Hadamard basis state. Okay, now we can walk through the whole scheme. So we have a bill, it has a classical serial number. Anyone can know this, it's generated by the central bank. We have a quantum state for that bill that the central bank produces by generating a classical bit string and generating random bases and then encoding it in the quantum system. Now, in addition to this, the central bank also needs to record the bases in which they perform measurement. So we can see, for instance, for the first quantum system, it's encoded in the computational basis. So the central bank records this information. They also need to record the measurement outcome. So we know when we measure in the computational basis that we should get a 0. This is all the information that the central bank needs when they receive a bill to verify that it's valid. We take the serial number, we perform measurement, and then we see if the serial number lines up with the expected classical information that we've retrieved through the measurement process. Now let's say we're a counterfeiter, and what we want to do is measure these systems, recover the classical information, and then encode that in a counterfeit bill. Well, in order to do that, we need to know the measurement bases. So here, let's say we start by incorrectly guessing that the first state is in the Hadamard basis. So we apply measurement. We're going to force the system to split into a plus or minus state. If it happens to be the minus state, then when we ourselves perform measurement as the counterfeiter, we'll get a 1, which is actually the wrong classical information. In addition to this, we've also changed the underlying quantum state so that when that bill is submitted for verification, it will behave probabilistically and it will fail verification half of the time. Now, this is a lot of quantum mechanical machinery to introduce just to have a piece of money. So there should be some good properties of this money that justify its existence. So here we'll talk about some of the most important ones. So the first is on the security side. It achieves what's called unconditional or information theoretic security if the quantum bill state is changed after each verification. And this result on the security analysis is due to my co-author and his co-authors. And what this means is that we don't have to make any computational hardness assumption. It doesn't matter if the counterfeiter has unbounded access to classical and quantum computational resources. They're still not going to be able to counterfeit any substantial amount of money by using one of these types of counterfeiting schemes that we described. Now, the other unfortunate property of this quantum money scheme is that it's technically infeasible, so it requires quantum memory with long coherence times, and this is one of the places in which we haven't seen substantial progress in the quantum technology experimental literature, whereas in other places we've seen big gains in the last 10 to 15 years. So, if we have a bill and we have quantum information, or we have classical information coded in quantum states, well, those quantum states decohere pretty quickly. And so it's going to be impossible to perform verification after a short period of time. Another property of Wiesner's scheme is that it requires online verification. So we actually have to communicate with a central bank in order to verify that a bill is valid. The final property of the scheme is that it's come to be called a private key scheme, analogous to private key cryptography, in the sense that the central bank actually has to retain private information about the bill's state and the measurement bases and outcome. And if this information leaks to the public, then the scheme itself becomes invalid. Someone can take this and use it to produce counterfeit bills. Now, in addition to private key schemes of the type that Wiesner introduced, we also have something called public key quantum money. And we had some primitive versions of this introduced early on, and it wasn't described as public key quantum money, but it's really introduced in Aronson in 2009. And he proposes 3 properties that are essential for having a high quality public key quantum money scheme. And the first is that quantum banknotes need to be able to be efficiently produced by a central bank. So we don't have a scheme whose security hinges on it being difficult to generate bills. The central bank can generate bills however they wish to satisfy their policy objectives. The second requirement of a public key quantum money scheme is that there must exist a polynomial time quantum algorithm for authenticating banknotes, which is completely public. Now, this piece is sometimes referred to as efficient local verification. And what this means is quite remarkable, and it's something that we can only achieve using money that exploits quantum phenomena. This is not possible in a classical setting. So specifically, what it means is that when we perform verification, we can actually do it locally. We don't communicate with a blockchain. We don't communicate with a bank. We don't communicate with the central bank. We don't communicate with a credit card company. If we have just 2 people and one has a bill and the other has the public key, we can actually perform verification locally, and we can also do it efficiently. So there's not an algorithm with a very long runtime and we have to wait. We can do this efficiently and locally, and this is categorically different from what we can do in the classical world. Now, finally, if a counterfeiter has access to K valid banknotes, they're not going to be able to produce an additional banknote with a non-negligible probability. So again, this is quite remarkable in the sense that the counterfeiter has valid banknotes, has a device that they can use to check whether or not those banknotes are valid, so they can alter the valid banknotes and apply and can apply the device to check whether the altered banknotes are correct. And even doing this, on a human time scale, there's very little chance that they'd ever be able to produce an additional counterfeit bill. Now, another contribution from Aronson 2009 was something called the complexity theoretic no cloning theorem. Now, what this does is it combines the no cloning theorem that we discussed earlier from Wouters and Zurich with Grover's algorithm. And if you're unfamiliar with Grover's algorithm, you can think of it as a quantum algorithm for searching for a needle in a haystack. So let's say we have a Boolean function that's a black box. So we don't know what this black box is doing with the Boolean string that it takes as an input. All we know is that for all inputs except for 1, it's going to return a 0. And for one of those inputs, it returns a 1. Now, if we think about, how do we go about finding the 1? Well, in the classical world, we can't do any better than just a brute force search. We iterate over all the bit strings until we find the one that outputs a 1. In the quantum world, we can use Grover's algorithm, and this does a little bit better. So we get a quadratic speedup. Now, after Grover, we actually got, we learned actually that the quadratic speedup is actually the best that you can do. So we can't actually do any better than a quadratic speedup in a quantum world for finding a needle in a haystack. And so Aronson cleverly exploits this in the complexity theoretic no cloning theorem. So specifically what the theorem says is that if we're given k valid random bills and we're given access to the black box verification device, then the number of queries that we need to perform to successfully generate a counterfeit bill is going to be proportional to root 2 to the n. And so what this means is that we don't get a substantial improvement over Grover, even though we have a bunch of valid bills that we can use. So this is equivalent to saying, if we have, if we know how the quantum bill is constructed in terms of the number of systems that it has and so forth, and we want to generate a valid quantum state so that the bill will pass verification, we can't actually do much better than just using Grover's algorithm to try to search through the states to find a valid bill. Having additional information actually doesn't do a whole lot for us. Additionally, if the number of qubits that make up the underlying state of the bill is very high, then the probability of success is going to be negligible. We can essentially ignore it. Now, there's some additional quantum money schemes that I won't say much about. There are quantum coins, which add an additional layer of anonymity. So quantum coins don't have a serial number, and they all have the same underlying quantum state. So we can't trace information about transactions that specific individuals do, as we can with bills that have serial numbers. We have quantum money schemes that make use of classical verification. So this means that we don't have to set up a quantum channel for communication between the central bank and every merchant. Additionally, it means that when we submit bills, when we submit information for verification to the central bank, we don't have to submit the underlying quantum state itself, which is subject to tampering that could invalidate the quantum bill. We also have some additional public key schemes. Recently, we had a scheme introduced that was based on knot theory by Fari et al., and also a scheme called quantum lightning, which is introduced in Xandri. Now, as far as the experimental progress side of things go, a variant of Wiesner's money was recently implemented in 2017 in a laboratory setting. And this specific variant is called optical quantum money because what they did was to take the pixels in an image of a bill and encode the information from those pixels in quantum states. Now, of course, this creates spatial correlation that can be exploited, and so they show with this scheme what an optimal counterfeiting attack would look like, but this does depart from the original Wiesner scheme, which achieves unconditional security. Bozio et al., which is my co-author, the group that my co-author Eleni is in, were the first to implement a quantum credit card scheme, and they rigorously demonstrated unforgeability of this scheme. So they've already shown that in the laboratory setting, they achieve a higher level of security than we could achieve with a classical credit card transaction as the variety that we use currently. They also show that it's compatible with recent advances in quantum memory. So this scheme can be linked up with that in the future. We also have recent work by Guan and co-authors, which implements a quantum money scheme in a laboratory setting that's based on the theoretical work of Amiri and Arizola. Now, the bottleneck for all of these schemes, and especially bills and coins, is quantum memory. These quantum states decohere fast, and we haven't had enough technological progress here to overcome this yet. Additionally, no public key schemes have been implemented, and even the theory behind public key schemes is fairly challenging. Okay, so we'll stop there with quantum money and move on to quantum algorithms in the second half of the presentation. So what we try to do in this section of the paper is to identify every quantum algorithm of relevance for economists, algorithms that could be used for econometrics, for computational economics. We try to explain how these algorithms work down to the pseudocode level. We try to explain some of the limitations of these algorithms. So there are very often substantial differences between the classical and quantum versions. And in order to find good applications for economics and finance, we have to know the limitations that we're working within. So we cover more than 10 families of quantum algorithms that are of relevance to economists. In the remainder of this presentation, I'm just going to concentrate on 4 of them that I think are particularly, or that demonstrate what it is that we're trying to achieve in the paper, or the value added that I think that we're able to provide with the specific approach that we take. So we'll start off with numerical differentiation, which is something that we use commonly in economics, especially in optimization algorithms. So often we need to compute something like a gradient or a Jacobian or a Hessian in order to either estimate a model or solve a theoretical model. And if we can't compute the closed form of the derivatives that make up the gradient, then often we'll rely on numerical differentiation. So let's say we have a function f that's differentiable and we want to compute its derivative at the point x. Specifically, we want to compute the partial derivative with respect to the argument xj. Then what we'll do is evaluate the function at the point x, and then we'll evaluate it at a nearby point where we increase xj by epsilon. We take the difference of those 2 functional evaluations, and then we divide by epsilon. Now, in addition to computing the numerical derivative, we also want to know something about the amount of error that it introduces. One way in which we can do this is to take the numerator of the expression for the numerical derivative, perform a Taylor expansion on it, and then rearrange it in terms of the partial derivative of f with respect to xj. So we can see that we do that going from equation 4 to equation 5. We can see that on the right-hand side of equation 5, the first term is actually the numerical derivative itself, and then the rest is going to be an error term. Now we can see the lowest order error term is the second partial derivative of f with respect to xj, and this is scaled by epsilon. So the error of the numerical derivative that we computed is going to be of order epsilon, and this is using the forward difference method. If we want to reduce that error at the cost of additional functional evaluations, then we can use the center differences method and increase that to of order epsilon squared. Now, in a classical setting, we typically don't just want to compute, well, actually in any setting, we don't typically want to compute just a single numerical derivative. We usually want to compute a gradient or a Hessian. And here, in order to compute the gradient, we're going to need to perform in a classical setting d+1 functional evaluations. The reason for this is that we have to first evaluate the function at f of x, the point at which we want to compute the derivatives. And then we have to compute a functional evaluation for each one of the arguments to f. Then in addition, if we want to compute higher order derivatives, so we want to compute the matrix of second derivatives, then the amount of functional evaluations we'll need will be of order d squared, because we have a d by d matrix. Now, the first quantum speedup for numerical differentiation was introduced by Jordan in 2005. And what Jordan demonstrates is that you can compute a d-dimensional gradient with a single functional evaluation instead of d+1 functional evaluations. And furthermore, to do this, you're going to furthermore, if you want to also do this for kth order derivatives, then you only need something on the order of d to the k-1 functional evaluations. So for a Hessian, we just need d instead of d squared functional evaluations. The precision of this scheme is determined by the number of qubits that we use in the quantum computer to perform it. Now, one thing that we might think immediately is that d is usually pretty small in models in economics and finance. So often d is 10 or something like that because we use these small models small models that are typically motivated by theory, but we do have areas in economics like structural I/O and labor and so forth, where we have models with many parameters. And additionally, we're increasingly importing importing models from machine learning, which often have tens of thousands of parameters. And so it could be the case that collapsing D down to 1 at some point will make it worth the overhead of interfacing with a quantum computer to perform this particular step in the subroutine. Now, I won't step through the algorithm itself, but this is just to demonstrate one of the things that we do in the paper. So we try to break the algorithms of interest for economists down to the pseudocode level so that you can see each subroutine that you need to implement. You can see here that in order to compute the gradient, you're going to need to apply both an inverse quantum Fourier transform and a quantum Fourier transform. So there are some common ingredients that will reappear in quantum speedups, including quantum Fourier transforms and also phase kickback and phase estimation. And so we have a separate section in the appendix that tries to explain precisely what it is these algorithms are doing so that you can get a sense of how quantum speedups are achieved and also understand the algorithms that you're most likely to use. Now, the next quantum algorithm that we'll talk about is one used for linear systems problems. So the first quantum speedup for this was introduced by Harrow, Hasidim, and Lloyd in 2009 for problems of the form AX equals B, where A is an n by n Hermitian matrix. If we don't have a Hermitian matrix, we can rewrite it easily enough as a Hermitian matrix, so this is an important limitation. B is a unit vector and X is a solution vector. Now, a classical algorithm requires time that is polynomial in n and of the condition number to solve for the solution vector X, whereas the Harrow et al. Algorithm reduces this to poly log n kappa. So we actually get an exponential speed up in n with the Harrow algorithm, although we still have dependence on the condition number that's still just polynomial in kappa. Okay, so another thing we do in the paper is discuss the limitations of algorithms, and there are important limitations when it comes to quantum linear systems problems. So here we talk a little bit about, this should actually be Aronson 2015, which provides a discussion of the limitations of the HHL algorithm. So the first and most important one is that the time needed is still growing linearly in kappa. So, we can look at the ratio of the max and min eigenvalues for our A matrix to get a sense of whether or not kappa is growing linearly, is still growing linearly in n, and if it is, then that's going to fully negate the speed up that we would get. And in fact, in most problems, this is actually going to be the case. So this is sort of a simple check that we can perform before we go any further with the HHL algorithm. It's just check the condition number of your matrix relative to the dimensions of the matrix. Now, the second limitation is that the output state is actually the quantum state X, not the classical vector, with the components X1 through Xn. So for instance, with OLS, we don't recover the coefficient vector directly. We have this quantum state, which roughly encodes the coefficients and amplitudes, but we're not allowed to access that vector. We can perform we can perform measurement on it to try to extract information about it, but we can't just grab, the whole X vector. We can't just get an arbitrary coefficient like Xj. In fact, to do that, we'd actually have to set up the same problem and solve it n times to be able to recover the value of a coefficient like J. So instead, what we have to do is think about what types of clever measurement we can perform on the X vector, on the quantum state X, to recover information that's useful. So we can, use it to perform to compute an approximate inner product, and then we're just recovering a single value instead of a coefficient, a vector of values. Now, there are two papers relevant for economists that do this well. So one is Wiebe et al. 2012, which performs OLS for a linear system using the Moore-Penrose pseudo-inverse instead of using the standard expression for OLS, where we have instead of using the standard expression for the solution to the OLS problem, we instead use a Moore-Penrose pseudo-inverse. And here what they do is, instead of trying to recover X, they recover the model fit, so that they still gain, they're still able to get an exponential gain on the runtime. And this allows them to compute model fit for, potentially thousands of models using the runtime gain. And then once we've identified the one that we actually want to estimate, we just do it classically. So that's one way to work within the limitations of HHL. Another one is just to produce conditional mean prediction. So we just interact our coefficient vector, or we compute the inner product of our coefficient vector with some data to produce a conditional mean prediction, rather than trying to actually recover the coefficients. Okay, so there are two additional algorithms. Two additional things I'll cover, and these are things that we wouldn't actually perform on a universal quantum computer. So these just make use of specialized devices that can only perform certain tasks. So the first is adiabatic quantum computing. And here what we do is exploit the fact that quantum systems are going to want to minimize the level of energy in the system. So they'll want to move to something called the ground state, which is the minimum level of energy. And what we can do is take a combinatorial optimization problem and rewrite it in the form of a quadratic unconstrained binary optimization problem, a QUBO. And then we can take the weights from the QUBO and embed it in the quantum system itself, and then let the quantum system discover the solution to the QUBO by configuring it itself in a way that minimizes energy. Now here, the weights that we're embedding in the system, those are shown in equation 7. So equation 7 shows the Hamiltonian, which expresses the level of energy in the system. And the information that we encode in that system is given by the QIJs and the CIs. These are the weights in the QUBO problem. And then the system finds the configuration of the binary variables, the xi's and xj's, which are zeros and ones. Now, there's one additional trick to adiabatic quantum computing, which is that how we actually do it is by starting off in the ground state by, instead of solving the problem we want to solve, solving one that has trivial values for Q and C, so that the system can very easily find the ground state. And this is because, just as we're, often get stuck in local minima, so does nature. Nature gets stuck in local minima. So we actually need to start in the ground state by choosing a trivial problem that nature can solve easily. And then what we do is, over time, mix the two Hamiltonians. So we mix the one that is using the trivial parameter values with the one that uses the true parameter values for the problem that we actually want to solve. Eventually, we arrive at the point where we're only using the Hamiltonian for the problem of interest. Now, the adiabatic theorem tells us that the Hamiltonian will remain in the ground state as long as the transition happens sufficiently slowly. Now, theory actually provides an explicit speed limit for this, although it can often be quite messy to compute it. Now, in practice, when we want to implement problems of this kind on quantum computers, we're actually going to be using a related process called quantum annealing, which is not the same. So with quantum annealers produced by D-Wave, for instance, we're actually not always going to be in the ground state. Now, these types of quantum annealers can solve combinatorial optimization problems. And in fact, we can rewrite some of the models that we use in economics as a combinatorial optimization problem. And there have been some applications of this, which at this point are more so proof of principle demonstrations. We're just showing that this is how it would be implemented on a quantum annealer. We're not necessarily solving a big problem. So we've seen this for financial crisis prediction, where it's done with, we try to predict a financial crisis using a dense banking network. Here we can embed the weights of that network in a cubo problem. Additionally, we could presumably make use of this to try to solve problems that involve global solution methods for computational economic models. Now, some caveats to using quantum annealing. When we can get this nice speed limit, but the speed limit may actually tell us that we have to move slowly enough so that it takes exponential time. So that's pretty bad news if we find that out. And it's also, it's not currently believed that they can solve the hardest types of problems, NP-complete problems, efficiently. So there's some cause for pessimism here in terms of solving problems that it seems like we probably can't solve efficiently in a classical context. Okay, now the last thing that I'll talk about is random number generation. So in the past in economics, when we wanted to do random number generation, we'd usually use something in the family of linear congruential generators. And these are simple pseudo-random number generators where a sequence of numbers is just generated using a deterministic process. So here we have some value x, and we just scale it by a, add c, and then we perform modulo division, and then we get the next number in the series and repeat the process. Now, the challenge with these LCG random number generators is that if, it really came down to choosing the right coefficients. So if we choose good coefficients, we get random numbers that look like the series in the bottom panel. And if we pick bad values of the parameters, then we get something that has a clear period. Now, one problem with LCGs is that we get a mix of this type of stuff and we don't always know what causes it. And there's a big literature identifying when it happens, but it's just one of the potential problems that can arise when we use an LCG and we need to have something that's essentially true randomness in our problem. Now, the Mercian-Twister algorithm has gained widespread use, and this is an improvement in some sense, but it has the same problem as pseudo-random number generators. We also have physical random number generators, but these make use of classical physical processes, so they're ultimately still deterministic. And they also have the disadvantage of having low throughput. So we generate numbers much more slowly with a physical random number generator than we do with pseudo-random number generators. Now, the final possibility is to instead use a quantum random number generator. And these are, in fact, already mature technologies. So you can purchase a quantum random number generator that's the size of a USB drive that you can plug into your computer for about $1,000, and you can actually generate true random numbers from this. So there are two advantages to a quantum random number generator. The first is that it relies on quantum physics, which is inherently probabilistic. So this is the only way we really get away from determinism and generate values that are truly random, that we don't have to spend a lot of time thinking about what might be the problem that arises from using this particular deterministic process. The other benefit is that some state-of-the-art quantum random number generators actually have throughput that's similar to pseudo-random number generators. So they actually do better than physical random number generators in that respect. Now, I'll abstract away from the specific physical implementation of these and just say how this would work in a general quantum circuit. So what this USB type device would do is it would prepare the state of a quantum system and something like the zero computational basis state. And then it would put that in a superposition using something like the Hadamard gate, where then in an equal superposition of 0 or 1, we apply measurement, and then it outputs a 0 or a 1 with equal probability. So we now have true random numbers drawn from a Bernoulli distribution, and we know from the statistics literature how we can build this up into other distributions like the normal distribution. Okay, so since the paper itself is mostly a survey, we're presenting a summary. I won't summarize a summary, and instead I'll just say, if you think that this project is interesting, please send me an email and we'll add you to the list and send you the paper as soon as it's available to circulate. Thank you for your attention.
Thank you, Azaya. This is a real service to the profession, writing this paper. A couple of questions. You didn't really talk, neither in the money part nor in the algorithmic part, about error mitigation problems. We know that qubits are prone to error. Does that matter for the discussions about quantum money, respectively, your random number generators?
So from my understanding, at this point, we have quantum random number generators that do I mean, we have essentially mature and commercial technologies available for that. So I'd say with quantum random number generators, it's not quite as much of a problem because the task that we're performing is simple. We just have usually like a single unentangled system, and we put it in a superposition and we perform measurement right away. It certainly is a problem for quantum money, so it introduces transaction failures and so forth. And this is something my co-author Eleni in the project that they work on, they take this into account. You know, the failures that will arise purely as a result of experimental imperfections. And this is certainly one of the biggest problems with algorithms as well. So we do have more of a discussion on this in the paper than I said here, but the short summary of it is that this is absolutely one of the biggest challenges, both with quantum money schemes and quantum algorithms.
Another question more about combinatorial applications is trade matching in say dark pools. Do you know of any sort of experiments so far in trade matching using quantum technology?
So I'm not actually aware of any. I mean, there could be stuff in progress in the quantum finance literature, but I haven't seen it yet.
Okay, thanks. There's one. Another question is, are the quantum RNGs actually truly random, or are they pseudo-random in the quantum domain?
So I guess I'm not quite sure what the,
I'm leaving the question.
There might actually be a very deep point to that actually that I'm missing, but I would say that the quantum random number generators are generating true randomness. And we actually have a higher standard of randomness called certified randomness, which we talk a little bit about in the paper. But I think the short answer is, as far as I'm aware, you could consider it to be true randomness in the sense that we're just taking a photon and putting it in a superposition and performing measurement. But there could be something there that I'm missing that's a bit deeper.
And a final question, in the interest of time, perhaps, is so I gather the Swedish central bank is your employer is interested in quantum applications. How is research in central banks, other than the Swedish central bank, focused on quantum money? Where are we in terms of, is there sort of is there momentum picking up on this topic, or is it still way out there?
So I think it's still way out there. So I'd say, even my employer, it's still way out there at this point. I'm really trying to introduce the concept, and of course, for the most part, we can't do this technically yet. So we can implement a quantum credit card scheme in a laboratory, and that's big experimental progress. But we're still not at the point where we could build a payment system that's specifically based on quantum money yet. So I'm pushing this at least to create awareness, but as far as I'm aware, there aren't any central banks that are specifically working on it, but it could be an interesting topic because now we have a lot of central banks who are thinking about implementing a central bank digital currency. And down the road, 10 or 20 years from now, if we have a workable theoretical scheme for public quantum money, and we also have the quantum infrastructure to implement it, that could give us a form of money with categorically different properties that are attractive for a number of reasons. So I think it's certainly something worth watching as this field develops. But I think at this point, central banks might be interested, but I don't think anyone's working on this.
Thank you, Isaiah. With that, I'd like to conclude this webinar. We are going to take a summer break, so stay tuned and check our website for the announcement of the next webinar on quantum computing applications in the financial sector, which will be taking place after the summer break. Thanks again to everybody out there for attending this webinar that is jointly organized by the Keating Institute at UNC Chapel Hill in the North Carolina State University IBM Q Hub. Stay safe and see you after the summer break. Thank you.